Today, we are diving into the really cool science behind reflections. You know, it's everywhere. From the mirror you look into every morning to, believe it or not, a simple kitchen spoon. The physics of light is all around us, and we're going to break down exactly how it all works.
But let's kick things off with a little puzzle, one I'm sure you've noticed before. Go grab a spoon and look into the curved part you eat from. Have you ever wondered why your reflection is upside down? It's such a simple thing to see, but it opens up this whole world of physics. Stick around because by the end of this, you'll know exactly why that happens.
So, to finally solve that spoon mystery, we've got to start with the basics. It really all comes down to the fundamental rules that tell us how light moves around, and, more importantly for us today, how it bounces off things.
First things first, we need to know the core principles. You can think of this as the official rulebook for light. See, when light hits any surface, it doesn't just scatter randomly. Oh no, it follows two very specific, very predictable laws.
And here they are. It's actually pretty simple. Law number 1. The angle that a ray of light hits a surface, that's called the angle of incidence, is exactly the same as the angle that it bounces off, which we call the angle of reflection. And second, the incoming ray, the reflected ray, and an imaginary line we draw straight out from the surface, called the normal, they all line up perfectly on the same flat surface. That's it. Simple, elegant, and it's the foundation for everything we're about to cover.
Okay, so we've got the laws. Now let's see how they work with the most common mirror out there, a regular flat or plane mirror. We all use one every day, but what's really going on behind the glass to create that image we see?
Well, the image you see in a flat mirror has 5 key things going on. First, it's virtual. That just means the light rays only look like they're coming from behind the mirror. You can't, say, put a piece of paper back there and see the image on it. It's upright, obviously, and it's the exact same size as you. It also appears to be the same distance behind the mirror as you are in front of it. And here's the fun one. It's laterally inverted. That's just a fancy way of saying your left and right are swapped. So, flat mirrors are pretty straightforward. But what happens when we start to bend the surface? This is where it gets really fun. We start to get those crazy funhouse effects that can shrink, stretch, and even flip our reflections completely upside down.
When it comes to curved mirrors, there are really 2 main types. Concave mirrors curve inward, kind of like the inside of a cave. They're great at collecting light and bringing it all together at one point, called a focus. Convex mirrors do the exact opposite. They bulge outward and make light rays spread apart, or diverge. That's why you see concave mirrors used to magnify things, like in a makeup mirror, while convex ones give you a super wide view, perfect for security mirrors.
Now, to talk about these mirrors like a pro, there are just a few key terms we need to get down. The pole is just the very center of the mirror's surface. The center of curvature is the center of the big imaginary ball that the mirror was sliced from. The focus is that special spot where all the parallel light rays meet up, and the distance to that spot is called the focal length.
Okay, I know this might feel like a lot of geometry, but here's the good news. Physicists came up with a really powerful and actually pretty simple way to figure out exactly what an image will look like without having to draw a single thing. I like to think of it as the mirror's secret code. And here it is. This is the mirror formula. It looks simple, but this little equation is incredibly powerful. It connects the focal length of the mirror to where the object is and where the image will show up. Just those 3 little variables can tell you almost everything you need to know.
So let's quickly break down those letters. F is that focal length we just talked about. U is the distance of the actual object from the mirror. And V is the distance of the image from the mirror. The beauty is, if you know any 2 of these, you can always find the third. So now we know where the image is going to be, but what will it actually look like? Is it going to be bigger, smaller, upside down? For that, we need the second part of our secret code, the magnification formula. It's just M for magnification, and it equals -V divided by U.
And this little m is amazing. It tells us the entire story. The sign tells you if it's upright or not. Positive is upright, negative is inverted or upside down, and the number itself tells you the size. If it's bigger than 1, the image is magnified. If it's smaller than 1, the image is reduced. It's a complete description of the image, all packed into one single number.
Alright, theory's great and all, but let's actually see how this stuff works in the real world. We're going to take these formulas for a spin and solve an actual problem. You'll see just how powerful this physics can be.
The method is just a simple 4-step process. First, write down everything you know. Second, pick the right formula. Third, plug in your numbers and solve it. And finally, state your answer. It takes a tricky physics problem and turns it into a simple recipe.
Okay, let's try this example. We've got a concave mirror, and we know its focal length, f, is 10 centimeters. Then we place an object, u, 15 centimeters in front of it. The big question is, where is the image, v, going to appear?
We just grab our mirror formula and plug in the numbers we know. So 1 over 10 equals 1 over v plus 1 over 15. Then, with a little bit of simple algebra to solve for 1 over v, we find out that it equals 1 over 30.
And there it is. We just flip both sides of that equation and we get our answer. V equals 30 centimeters. That means our image is going to form 30 centimeters away from the mirror.
But what does that result really tell us? Well, because that image distance v is a positive number, it tells us the image is real, meaning you could actually project it onto a screen if you wanted to. And if we went and calculated the magnification, we'd find out it was negative, which means the image is also inverted. It's upside down.
And that brings us all the way back to our spoon. The inside of the spoon acts just like that concave mirror we were talking about. When you hold it far enough away, you're creating a real and inverted image, and that is why you're upside down. Now go ahead and flip it over. The back of the spoon is a convex mirror, which always makes a smaller, upright, and virtual image. Two different mirrors, two totally different reflections, all in one spoon.
So there you have it. The physics of reflection isn't some abstract thing stuck in a textbook. It's right there in your car side view mirror, a shiny Christmas ornament, or the back of a soup ladle. Now that you know the rules of the game, where else can you spot these cool funhouse effects